Hello, good day to each and everyone. So this is Physics 131. Ladies and gentlemen, I am Hanif M, and the topic that was assigned to me was example 3.2 and 3.3. So I'm sorry. So we have here, I will be in here, we'll be going through this example 3.2 and 3.3. Specifically, example 3.2 is about um, uh, under damp oscillation, and example 3.3 is about critically damped situation. Okay, so okay, we will be example 3.2 we have here. Construct a general phase diagram analytically for the damp oscillators, then using computer make a plot of x and time derivative of x versus time and a phase diagram for the following values. We have here we have here a magnitude A is equals to 1 centimeter, and the omega sub O is equals to 1 rad per second, and beta is equals to 0.2 seconds inverse, and um and uh, second inverse, and we have here the delta is equals to pi over 2 rad. So we have here solution, no? So first we write the expression for the displacement and velocity. So this equation here have already discussed by our instructor, no? So this is the equation or the general solution for the uh over damp oscillation case. Okay? So what I mean is under damped oscillation. So as you can see here, we have here a component of sinusoidally, and at the same time we have here a component of damp na case. Okay, so it means that under damp oscillation is a combination of damp and oscillation. Okay, so that's why it is called as an under damp oscillation. Okay. So since we are required to have the time derivative of x, if we take the derivative of that, we have this a situation, or we have this equation. Now, since this x of t and x dot of t are very hard to manipulate, no, or to have its graph, we need to uh, reform this into another form of equation, but but we will just use that one in just we will just use that to graph this situation or to graph this example. Okay, so by taking u is equals to omega 1 x, and w is equals to beta x plus time derivative of x, and substitute the value of x and x dot, we will have this equation. Okay, so as you can see here, it reduces this equation reduces into a equations which just contain a cosine and sine term. Okay, so in that case we can just use a some technique to graph that. Okay, so if we take the if we represent u and w in polar coordinates, then rho, which is the magnitude, is equal to square root of u squared plus w squared. Okay, so and phi is equals to omega 1 t. So thus, rho is equals to omega 1 a e to the power of negative beta over omega 1 phi. Okay, so try it. No, if you will use the value of u and w as what we have just derived in here, ito yan siya, itong dalawa, by just using this magnitude, no, or pwede rin gamitin nyo to siya, no? Then you after that you just use a, di ba, cosine squared plus sine squared is equals to 1. So gagamitin niyo yun siya para ma-reduce yan siya into this form lang, okay? Into this form where phi is equals to omega 1 t, okay? Or typically this just the magnitude of u and w. Now as you can see here, the graph of the relationship between the w, u, and rho in terms of their graph is just the magnitude. Okay. Okay. So which is this equation is the equation of logarithmic spiral, because the transformation from x and x a logarithmic spiral, no? So then since the transformation from x to time derivative of x into u and w is linear, the phase path has basically the same shape in u and w. Okay? So this is just a same lang sila ng relationship, which are all a logarithmic spiral because we use a linear transformation from x and x dot to u and w. Okay, which are both shown in the figure 3-10a and 3-10b. So they both show a spiral phase path of underdamped oscillator. They continually decreasing in magnitude of the radius vector of the representative point in the phase plane always indicates a damp motion of the oscillator. So as you can see here, no, they are both spiral spiral logarithmic in situations, which suggests that in the underdamped situation, the situation will just go an oscillation, and eventually it will go to zero. Okay? So yun yung situation natin dito actually sa example 3.2. Once again, in underdamped situation, um, the oscillations will go farther uh, and eventually go to zero. Okay, so it means that it will reduce its magnitude and the energy associated with it, and eventually goes to zero. Okay, so that's why the graph of x dot and x here is a spiral oscillation, no? Okay, so to suggest that the energy and the amplitude is going to zero talaga. Okay, so yun. So, and then if you take the graph of x and x dot as a function of time, you will know that the graph is taking an oscillation, but uh, for some value of time, it will go to zero. Okay, it will go to zero. So yun. And for the time derivative also, it will also take an oscillation, but at some value of time t, it will just go to zero. Okay? So yun yung situation natin for the underdamped situation. Okay. So the actual calculation using the number can be done by various means with the computer. So we choose to use one of the commercially available numerical programs that has a good graphics output. But since we have not yet tackled the application in the programming, okay, we will just assume that if you take the graph of that equation, just what we have derived, you will go to this results na spiral yung ating situations or yung ating graph. Okay? And you will find out that in the underdamped situation, the case is reducing, no, their magnitude is decreasing, and at the same time the stored energy in that motion is also decreasing. Okay? So okay. So the weak damping parameter beta allows the system to oscillate about zero several times before the system finally spiral down to zero. In this case, no, the system crosses the x equals to 0 11 times before x decreases finally to less than 10 to the negative 3 of its maximum amplitude. The phase diagram of figure 3-10b displays the actual path as what we have as what I have said, no. It will just cross the x is equals to 0 na situations, and in 11 times before it goes to 0. Okay, so that's the case for underdamped situation. Okay, so now let's go to example 3.3. So typically this example 3.3 is about uh, critically damped na situation. Okay, so later you will know that in this case, this is a critically damped situation. Okay, so consider a pendulum of length L and bob of mass M at its end. So moving through oval with T decreasing, the massive bob undergoes a small oscillation, but the oval retards the bob's motion with a resistive force proportional to a speed with F resistive is equals to 2m square root of G over L multiplied by L theta dot. The bob is initially pulled back at t is equals to 0 with theta is equals to alpha and theta dot is equals to 0. Find the angular displacement theta and the velocity theta dot as a function of time and sketch the phase diagram if j over l is equals to 10s inverse and alpha is 10 negative 2 rad. So solution. So we have here um, gravity produces the restoring force and the component pulling the bob back to the equilibrium is mg sine theta. So this has just been shown by our instructor that uh, the component of the weight of the bob will tend the situation to go its oscillation, no? So along the oscillating path, no? So this is the component. So Newton's second law become force, which is equals to mass times L theta double dot is equals to restoring force plus resistive force. Situation here, um, this situation here is same as mass times acceleration, where theta or where this L theta double dot is equals to acceleration. Okay, so why I have said that? No, because in the pendulum case, no, the x, no, the movement na parang pa-spiral is equal to, I mean the movement na parang ano yun, pa-circular is related with the linear related with the angle, no? So that is related as a uh, uh, x is equals to length times the theta, di ba? So that is I don't know what is the name of that equation, no? So yung basta relationship yun siya ng theta at saka yung arc, no? So x is or c is equals to length times theta. Okay, so if you take the derivative of arc, we have uh, in this case we just take it as x dot is equals to l times theta dot, and if you take another time derivative, we have x double dot is equals to l times t double dot, and we know that x double dot is the acceleration. So therefore, in the pendulum case, the acceleration is equals to l times double dot. Okay, so I have sorry for not showing that here explicitly because um, I was not prepared or I don't know how to use a pen here. No, it's because I'm just using a phone to have this report. Okay, so I hope you have already understand that how to find this acceleration here. Okay, now substituting the value of restoring force and the resistive force, you have this final equation of motion. Okay, so um, then if we check the value of or check that the force direction is correct depending on the sign of theta and theta dot. For small oscillation, we have sine of theta is approximately equals to theta, and equation 3.46 becomes theta double dot plus 2 square root of g over L theta dot plus g over L theta is equals to 0. Okay? So, this is from the equation here. Okay? So, you just have to cancel out the mass here and then divide both side by length. Then, eventually, you will get this equation. Okay? You will get this equation. Now, if we compare this equation into equation 3.35, no, this equation 3.35 has been discussed by our instructor, no. Please remember that this is the equation for the general case of oscillation or damp oscillation. We have the x double dot plus 2 beta uh, times x dot plus omega sub o squared x is equals to 0. Okay, I hope you will still remember that. Okay, so we have in by comparing that 'di ba in here, 'di ba yung sa previous na equations natin ang nakalagay rito is 2 beta and dito siya isang nakalagay dito is omega sub o squared. Now if you will take the beta as equals to square root of g over L, no? You will notice that beta squared is equals to g over L, and omega sub o squared is also equal to g over L. So therefore in this case, omega sub o squared and beta squared are all equal to g over L, therefore they are equal, no? And you found out that in this case, this is a critically damped na situation. Okay? Critically damped na situation. Then after being initially pulled back and released, the pendulum accelerate and then decelerate as theta goes to zero. The pendulum moves only in one direction as it returns to its equilibrium position. Um, 'Di ba, from the discussion of our instructor, um, she showed that for the underdamped situation, it will go to after you release the oscillating body, it will go to some oscillation and reduces its magnitude and after before it goes to zero. And for the critically damped na situation, after you release the oscillating body, it will not go to the other side. It will it will just tends to go to zero suddenly, no? For the overdamped situation naman, it will go to the other side shortly, but it suddenly goes to zero, no? So here, no, 'di ba kanina I have already shown that for the underdamped situation, yung graph ko kanina na nag-oscillate muna yung object before it goes to zero. Then in here naman, we showed that for the critically damped, as what our instructor said to us from here discussion, okay, if you release the object from what position you have take, okay, in having that oscillation, it suddenly goes to zero, okay, and not goes to the other side. So same as what we have, same as what example says here, no? So sabi dito, the pendulum accelerate and then decelerate as theta goes to zero, no? So parang hindi na siya nag-goes to the other side. The pendulum moves only in one direction as it returns to its equilibrium position, no? So, here's the situation, no? We have here the pendulum, then meron tayong magnitude na mg sin theta. Ito yung nagpapa ito yung nagpapatik ng kuan, no? Oscillation, itong component na to. And we have here also the component of along here we have here a component of mj cosine of theta. Okay? So, we have here the situation. And this is the ano yun? Tawag dito, um, resistive force, no? So if we take the graph of theta dot and theta by using this equation, no? By using this equation, theta dot and theta, I mean, if we take the by taking the solution of this general solution here, no? General equation here. By taking the solution of this one, okay? So let us muna hindi muna mamaya muna natin 'to i-discuss, no? By taking the solution of this equation here, okay? Um by taking the solution of that, over you will find this equation here, no? So this equation, okay, since 'di ba yung sa general solution natin for the general equation for damp oscillation, meron tayong square root sa right side, 'di ba? If I'm not mistaken, yung square root na yun is may nakalagay doon na beta squared minus omega sub o squared, no? So in this situation, since it is a critically damped situation and beta squared and omega sub o squared are equal, therefore the quantity inside the square root is zero. So ibig sabihin, the general solution are all real number, okay? Are all real number. So in the differential calculus, if the solution are all real number, okay, then you will take the function as a exponential, no? Exponential. But since if you will not take another quantities here, this should be equal, no? So then magre-result kay 2 e or 2, then yung magnitude niya ito the negative bit theta. So para ma-distinguish natin yun siya, we will add another quantity which is time, no? So as you can see here, the resulting theta of t is equals to a plus beta, a plus b t e to the power of negative b theta. Okay, I mean b time. Okay? So yan. So ito na yung general solution natin. Now, for us to be able to get the magnitude a and b, we will use the initial values, no, na stated na doon sa problem natin. Okay? So, as you can see here, if you use the initial values, you will know that the value of A is alpha and the value of b is equals to um, alpha multiplied by beta. Okay? Then substitute that one in the original equation of this theta of t. So we have this equation. Okay? Now, if we take the time derivative, we have this equation. Okay? We have this equation here. Okay? If we take the time derivative. Now, by using this equation 3.49 and 3.50, we can actually have this equation, have this graph, no? Okay? By using a graphing tool or a computer programming, okay, we will know that this is the graph of the critically damped na situation. As you can see here, no, after the mass undergoes its maximum value, it suddenly goes to zero. Okay, and it will not go to the other side anymore. Okay, so it suddenly goes to zero. Okay, so ibig sabihin, yung resistive force natin is larger enough to compensate the motion of the oscillating body from going to the other side. Okay? So yun. So once again, it goes to the higher maximum value, then it goes to zero na. Okay? So hindi na siya pupunta sa the other side na situation. Okay? That's the situation for the critically damped na situation. So I think that's all. Correct me if I'm wrong, ma'am, no? Kasi this is just also my research about what we have in our topic. Okay? And I'm just a student, no? Also tackling this topic. So anyone who can know that I'm wrong about my discussion, please correct me if I'm wrong. Okay. So I think that's all. I hope this informs a lot. No, this informs us a lot about our topics, and I hope this serves as our guide to to understand fully the discussion or the topics that we are tackling right now. Okay, so that's all. Good day. Have a nice day, everyone, and assalamu alaikum.